Hello friends, welcome to this video. In this video, we'll be discussing this TY practical question on linear algebra. Eigenvalue and eigenvector is nothing but topic. The question is, if my V is a non-zero vector in Rn and A is nothing but the matrix obtained after multiplication of V transpose with V, where here we consider V as a 1 cross n row matrix. We need to prove the following three things. The first is eigenvalues of A are 0 and V transpose. Other thing is we need to talk about the eigenspace of V transpose and also identify the eigenspace corresponding to 0. So what we do is we just try to write the solution of this. Before writing the solution, let us just have some observation about this A. Right, the first thing is my V is a row matrix of the dimension 1 cross n. That means the dimension of V is 1 cross n. That means the dimension of the V transpose would be what? The dimension of V transpose would be n cross 1. Now, if my A is same as V transpose V, then the dimension of this A would be what? It would be an n cross n matrix. I just increase the thickness. So it is n cross n matrix, right? So my A is an n cross n matrix. Now in the question somewhere, they are asking me about VV transpose as well. So let me just talk about that. So my V transpose, over here I have V. So the dimension of this is nothing but 1 cross 1. That means it is going to be a number. More precisely, this is nothing but the norm of that vector. Because if I have a row matrix over here, if I multiply with the same thing but in the column form, after multiplication, what I get is nothing but norm of V the square. Correct. So these are the few things that we might need for the proof. So what we do is we just start the proof with this as our base, that these are the things that we know. The first thing is to prove that 0 is an eigenvalue and VV transpose is the eigenvalue of it. Okay, so we start the proof in a simpler way. First, I start that my VV transpose should be an eigenvalue of it. Now, a real number will be an eigenvalue if I can find out corresponding eigenvector, right? So I start thinking about what could be the eigenvector for this V transpose. If this is an eigenvalue, what I know is I observe that this is actually same as my norm of V square. For this eigenvalue, I am thinking about eigenvector, right? So what I have A times something should be same as V transpose times the same thing, right? Is it correct? We want to find out the eigenvector for this eigenvalue. I already know the eigenvalue. I'm just interested in that x. What is the condition on this x? The condition on this x is my x must be not equal to 0. Let me consider this x to be the given vector v itself. But V is what? My V is nothing but a row matrix. So I just wanted the column matrix. So I consider V transpose. Right? Suppose if I consider V transpose, what I get, let me just try to see what is going to be V transpose. Right? So what I have my AX is same as, what is A? A is nothing but V transpose V. I have to multiply this with V transpose. Right? On the place of A, I write it definition. Since we know this multiplication of a matrix is associative, I can write this is same as my V transpose V transpose. Right. So this is same as what? This is same as A times V transpose. So A times V transpose is same as this. This is something that we wanted, right? This is something that we wanted. What I found is my A times V transpose is same as this inside bracket is nothing but norm V square. Since it is going to be a number, I can write it ahead. Now this is same as V transpose. Hence, my this V transpose becomes an eigenvector for eigenvalue this. Therefore, my V transpose is the eigenvector for eigenvalue that was required, that is VV transpose, right? So first part of the proof is done. That means I wanted to show that VV transpose is an eigenvalue of it. Yes, I found that it is an eigenvalue and it has eigenvector as what? The eigenvector is nothing but V transpose, right? So we can answer the second question as well. Show that the eigenspace corresponding to this eigenvector, this eigenvalue, that is VV transpose, is of dimension 1. What we got that? We got that the V transpose is nothing but the eigenvector for eigenvalue VV transpose. While solving this, we are not getting any other eigenvector at present, right? So it might be possible that it might have some another eigenvector as well. Is it possible? A single eigenvalue could have a multiple eigenvectors. Yes, it is possible. So still we are thinking how I can prove that if dimension could be 1. Right. So we will answer this question, why the eigenspace of VV transpose has dimension 1. To answer that, we will think about now the other eigenvalue, that is nothing but 0. Now 0, I want to show that the eigenvalue for A is 0. How we can prove that? That means I need to find out x such that A times x is same as 0 times x, where this x is not equal to 0. Correct? I need to find out such x so that A times x is same as 0 times x. What do you think about this? If I want to prove that A times x is same as 0 times x. Now what is A times x? A times x is what? It is nothing but A is same as V transpose Vx. I need to prove this must be equal to 0 times x, that is nothing but 0. What could be this x? What I can write? I can write this is same as V transpose Vx. Suppose if my V transpose x came out to be 0, my answer is something that I want. Now V into x is 0. That means what? That means the inner product of V with x is 0. Now if the inner product of V with x is 0, that means my x must belong to where? X must be orthogonal to V. So what we consider is, we consider x be any orthogonal vector to V, then my V times x would be equal to 0. Then if my V times x is equal to 0, then V transpose V times x, this came out to be 0. Therefore, I can write V transpose V times x equal to 0. Therefore, my Ax is equal to 0 and this 0 can be written as 0 times this x. Hence, this implies me my x is an eigenvector. X is an eigenvector for eigenvalue 0. So my 0 is also an eigenvalue with corresponding eigenvector as x. But why x is what? X is nothing but an orthogonal vector to V. Now question arises, will there be existing a non-zero orthogonal vector to V? We need to answer this question, right? So we answer this question now, but we go ahead to this page. So what I'm thinking now the question that asks is, will there exist x orthogonal to V? That is a question mark. So what we start thinking, what are the things that I know? I know that my V is a non-zero vector, right? V is a non-zero vector. That means if it is a non-zero vector, I can say that singleton V is linearly independent. Correct? It is a linearly independent, and what I do is, by using this V, I generate a subspace. Means all the scalar multiples of V, and those scalar multiple of V becomes a subspace S. That means this S is a subspace of V where it is generated by single element. That means my dimension of this S must be equal to 1. Now what we know is, we know that if I have a set, if I have a subspace, then the orthogonal complement of a subspace satisfy a particular condition. What is that condition? The condition is my dimension of S plus the dimension of the orthogonal complement of S must be same as the dimension of the domain in which we are working. Actually, this capital V subspace is actually nothing but the Rn. We are working in Rn, right? Is a dimension of Rn. So dimension of S I know 1, dimension of complement, orthogonal complement I don't know, but I know this is same as L. Therefore, what I found is my dimension of S complement must be same as n minus 1. That means set of all vectors which are orthogonal to this S is of the dimension n minus 1. So definitely, since my S complement is of the dimension n minus 1, it should have a non-zero element, right? So there will exist X orthogonal to V because my X belongs to S orthogonal complement and this is of the dimension n minus 1. If it is of the dimension n minus 1, that means there exists at least n minus 1 non-zero elements, right? Because it has a basis with n minus 1 element. So while answering this question, we answer so many questions together, right? First of all, we started talking about why that X exists, right? Non-zero X. That orthogonal vector, why that orthogonal vector exists? Because that orthogonal vector belongs to the orthogonal complement of S, which is of the dimension n minus 1. Hence, there exists a non-zero X, which becomes a eigenvector for us. Hence, 0 becomes an eigenvalue. Apart from this, we also identify what is the eigenvector for eigenvalue 0. The eigenvector for eigenvalue 0 is nothing but collection of all orthogonal vectors to V. That becomes a eigenspace for eigenvalue 0. Now, if I have for 0, the eigenspace is of the dimension n minus 1. For the other eigenvalue, the eigenspace will be of the dimension remaining part. That means n minus 1 is covered. The only dimension left is nothing but the 1. This is one more result that we are supposed to prove, that sum of the geometrical multiplicity should be same as the dimension of the domain. What I found is the geometrical multiplicity of 0 is n minus 1. Therefore, the geometrical multiplicity of the other eigenvector should be same as 1, because ultimately the sum should be equal to n, right? So there is one more result that we are supposed to prove, that the geometrical multiplicity of eigenvalues should added to the dimension of the domain, right? So by using that result, we can conclude that yes, the dimension of VV transpose is 1 because the dimension of eigenspace corresponding to 0 is n minus 1. So in this video, I was just trying to explain the result. I know I haven't wrote the proof properly, but the concept is something which need to be clear, right? So thank you so much guys for watching this video. If you like the video, please share it with your friends, subscribe to the channel and nothing else. Okay, bye bye.